Hey guys, this is your first video for your Chapter 3 notes that we have. We're going to start off with some basic exponent properties and solving some problems involving exponents today. So by this time, you should have completed the Chapter 3 intro worksheet, and all that worksheet did was just kind of like refamiliarize you with vocabulary, base, exponent, powers, things like that, keeping in mind that exponents are just repeated multiplication. That's all it does. So when taking a look at the basic exponential functions, we've got y equals, that's normal, and we've got some number here, some constant to the x power. So this is a constant. Remember, you can plug in numbers for x and you get a different result for y every time. So I can plug in 0 for x. I can plug in 1 for x, which means this number to the first power. I can plug in 2 for x, which means this number to the second power, and so on and so on. As long as this base is bigger than 1, it'd be kind of silly for the base to be 1, right? 1 to the first, 1 to the second, 1 to the third, that's silly. So as long as your base is bigger than 1, this is what the graph of pretty much any exponential equation looks like. This can be y equals 1.5 to the x. It'll pretty much look like that. This could be y equals 2 to the x. It'll pretty much look like that. Y equals 3 to the x. Your graph will pretty much look like that. Y equals 10 to the x. Okay, it might be a little steeper, but it's still going to pretty much look like that. Okay? So whatever your base is, as long as it's bigger than 1, that's what your graph is going to look like. Now, here's something that's really cool. It doesn't matter what your base is, 1.5 or 2 or 3 or 10 or 100, it doesn't matter. Plug in 0 for x, what do you get? Well, when you take any number to the 0 power, you get 1. So it doesn't matter what your base is. The point 0, 1 is always going to be on this graph, no matter how steep it is, no matter if our base is 2 or 100. This ordered pair is going to be on the graph of an exponential function. I think that's kind of cool. So here are some things that you're going to need to memorize. You're going to need to memorize like the basic, what a basic exponential equation looks like. You're going to need to memorize what the graph of an exponential equation looks like. And you need to memorize that you have a very important point on that graph. And it is 0, 1. Memorize that. Lock it in. Okay, now I mentioned that all this works when b is greater than 1. What happens if b isn't greater than 1? Well, I'll show you, but I don't want you to dwell on it. I don't want you to memorize it. Just think about it for about 20 seconds. When your base is a fraction between 0 and 1, it changes the shape of the graph. So when your base is like 1/2 or 2/3 or 7/10, the shape of the graph looks like this. Or when you put a negative in front of your exponent, that does the same thing as a horizontal reflection. So that would reflect the graph. Okay, so when we put a negative on our x or when we make that a fraction, that's when the graph looks different. Okay, I don't want you to dwell on that. This is what I want you to dwell on. This is what I want you to memorize. Okay, now let's do some basic exponent calculations in our head. Ready? We're going to take 3 and we're going to raise it to the -4 power. Well, keep in mind that right now, without it actually being inside a fraction, we know that this is in the numerator of a fraction. I can put it over 1. And what you're able to do is anytime you have a negative exponent, you can move the base and the exponent. We don't want to detach them from each other. We can move these from the numerator to the denominator or vice versa. Whenever we move them, our exponent changes sign. So I can move this to the denominator and look what it does to my exponent. It turns my exponent positive. So therefore my answer to this problem is still 1 over 3 times 3 times 3 times 3. So 3 times 3 is 9, times 3 is 27, times 3 is 81. 1 over 81. I want you to be able to use fractional exponents, okay? So I love this demonstration. So the exponent on my 27 is 2/3. That's a fraction. This is Mrs. Cambrin's idea. When she has fractional exponents, she likes to teach flower power. So if you think of the fractional exponent as it would look if it were a flower. So here's the ground, here's the grass. Anything below the grass would be like roots of the flower. And anything above the grass would be the flower itself, okay? So flower power. This, where your flower goes, this is your power. This is your root. So we're going to do a power of 2 and a root of 3. A power of 2, flower power, a power of 2 and a root of 3. So here's what we're going to do. We're going to third root, cube root 27, and we're also going to raise that to the second power. This is what it looks like. Cube root to the second power. Okay? And we often like to root it first. I don't want to square 27 first. Who wants to do that in their head? Nobody. So let's cube root 27 first. We all can figure that out. What number can I multiply by itself 3 times and get 27? 3. So we're going to cube root the 27 first to get a small number, which is 3. Then you can square it, and you can get your answer as 9. Okay? Flower power. This is your power. This is your root. When you've got exponential fractions in your exponents. All right, next problem. It gives us a function. All you have to do is plug in a number, and it says let's take 1.026 to the x power. We're going to do exponents first, and then multiply by 574. Your calculator knows this. It's going to do it for you. All you have to figure out is what to plug in. So this is one of those weird problems where it says, you know what? Don't just plug in your year. Don't just plug in your year. Let your years be years after 1974. So I did a little calculation over here. If I want to know, if I'm tempted to plug in 2028, but I'm not going to, I'm going to subtract 1984. So here it's been 54 years since 1974. This is what I want to plug into my function. So when you write it on your paper, you write it like this. You say, hey, I'm plugging in 54. Okay, then plug in 54. Then grab your calculator and type it all in at once. You should get 2,295, and don't forget it said it's in millions. So we have to write million on the end of that. All right, more exponent problems. We're going to use the one-to-one property. So the one-to-one property, here's what it means. It just means, hey, let's get the same base on both sides. So over here, I see that my base is obviously 2. I colored it in blue for you. Our base is obviously 2. What I want you to do over here is, how can you write 16 as a number with a base of 2? So I kind of want this to match. So I can write 16 as 2 times 2 times 2 times 2. I can rewrite 16 as 2 to the 4th. Once these two sides have the same base, do you see how they almost look the same? See, this is the same. Well, common sense tells me if these are equal and my bases are the same, well then my exponents have to be the same. So I just grabbed my exponents. I grabbed this exponent and this exponent, and I set them equal to each other, and I solved it. Super simple. As long as I can get the same base on either side. Let's look at another one. I want to change these so that they have the same base on both sides. So obviously my base is 5. I wonder how I can write this with a base of 5. Well, I can write 125. I can write what's in the denominator with a base of 5. So to get them to look the same, how about we move this up to the numerator? So when I move this from the denominator to the numerator, oh, well, I changed the sign on my exponent. Remember, any movement changes the sign on your exponent. So this becomes 5 to the negative 3. Now, common sense will tell you, if these two things are equal and these are both a 5, then my exponents have to equal each other. I wrote them down, set them equal to each other, and solved it. Last one. Same thing. I recognize, hey, look, I have a base of 4. So let me try to get this written with a base of 4. Is this 4 to the first? Obviously no. 4 to the second? Oh, shoot, too much. Well, now what? Well, now don't use a base of 4. What's something I can change both of these to? Well, I can change the 4 to a number with a base of 2. And I can change the 8 to a number with a base of 2. So here's what I decided to do. The 3x still has to be there. I just changed my 4 to 2 squared. Okay, so this used to be 4. There's my 4. Still, I have it to the 3x. And then my 8. That one was kind of easy. My 8 is 2 to the 3rd. Now, think way back. Algebra 1. Remember when you take a power to a power, do you remember what you do to these exponents? You multiply them. So this becomes 2 to the 6x. 2 to the 6x equals 2 cubed. Look, they're the same. They have to be equal to each other. Grab your exponents, set them equal to each other, and solve. X is equal to 1/2. The number e, I know you have some experience with the number e. It's irrational, just like pi is. So you all know pi is 3.14. You need to know that e is about 2.7. It's an irrational number. It's approximately 2.7. Your calculator knows exactly what it is, just like it knows what pi is. So I have this function, and again, we're looking at x. Let me think about this. Yeah, x stands for years. But be careful, it doesn't want you just to plug in the year. It says, whoa, plug in years after 1978. So instead of plugging in 2018, I'm going to plug in 40. So here's what I do. I say, I'm going to plug in 40. And then I did a rewrite and a rewrite. And look, I plugged in 40. And I typed it on my calculator. Kind of get used to using scientific calculators, because that's what you're going to use on your test. Your e to the is like 2 buttons under your second key. You've got an e to the button. Make sure you can type all that in at once, and rounded, you get about 4201. Okay, so that's just a little bit of like working with exponents and things like that. On the back is all about banking, and I know that you've done some problems with banking before, and this is a large part of what we're doing in Chapter 3, so I want to make sure that you get